So we started yesterday with an introduction to relations and functions. This entire unit, Unit 2, will be talking about one specific type of function, specifically linear functions. And one key characteristic that separates a linear function versus all the other different types of functions we'll talk about in Algebra 2 is that it has a constant slope. And that's sort of the topic of this section. What is slope? How can I calculate it? Why is it so important? So here's sort of like the definition of slope. The slope of a line, and beyond any rational logical reason, the variable that we typically use to denote slope is m, because, when you think of slope, you think of the letter m, of course, is the ratio, and the word ratio just means fraction, so it's a fraction or a division problem, is the ratio of the line's vertical change, and the, middle school pre-algebra word we use for vertical change is the, quote, rise, to the horizontal change. And the middle school pre-algebra term that we use for horizontal change is run. So that's why in your previous classes you probably heard slope being defined as, slope is just rise over run. But to use technical language, it's the vertical change to the horizontal change. Graphically, it looks something like this. So just draw a random coordinate plane. And I'm just going to draw a random line. There's no rhyme or reason why this line is what it is. I'm just going to draw a random line. Say, like there. If I take a look, and in this coordinate system is an XY coordinate system, if I just go ahead and take two random points on that line, say here, this here, the definition of slope is the ratio of the vertical change. So if I take a look between these 2 points here, that is the y value of that second point, that is the y value of the first point, and this guy here is his vertical change. If I take a look at the x value of the second point, if I take a look at the x value of the first point, that right here is his horizontal change. So the verbal definition that I gave you before, all it says is slope equals whatever that number is, that length, divided by this length. Right? So that's all slope is. You take the change in the vertical, that greenish, orangish color, and you divide it by the change in the horizontal, that bluish color. Now, of course, this isn't useful for us because we're not going to have green and blue, and we want numbers, we want math. So there is a formula, there is a way to actually calculate slope, and we, not surprisingly, call it the slope formula. Notice how when we calculate slope, it's always between 2 points. Right? You can't have slope unless you have 2 points. So the slope between the points, and you know how coordinates are some x value, y value. So I'll just say some x sub 1, comma y sub 1, and x sub 2, comma y sub 2 is calculated by The very famous Algebra 1 formula. M equals, M being slope, y sub 2 minus y sub 1 over x sub 2 minus x sub 1. If there is a thing to put on your note card for a future quiz or test, this would be a good formula to have. This is the slope formula. Very easy to use, but I've had students in the past get it wrong because they make silly little mistakes. So here are my hints. Here's my suggestions to you if you know you're the type of person that makes silly little mistakes. So for example, find the slope of the line that passes through -1, 3 and 2, -1. So I'm going to put myself in the shoes of a student that, you know what, math isn't my thing. I always make little mistakes. I always get points marked off because I do stupid things. I know I'm going to mess up the slope formula. Here's my hint to you. If you are that type of student, label everything. Now, it doesn't matter which one is the 0.1 or which one is 0.2. It really doesn't matter as long as you're consistent. So I'm going to go, okay, you know what? This is my x1. This is my y1. So this must mean my x2 and y2. Okay. Label, label, label if you know you screw up when it comes to substitution. My second hint, and this is a universal hint. I don't care if you're in my pre-algebra class. I don't care if you're in my calculus class. My hint is anytime you do any substitution whatsoever, use parentheses. So I'm just going to follow this formula up here. I have everything labeled. I'm just going to follow the formula. So M equals y2, which is -1, minus y1, which is 3, all over x sub 2, which is 2, minus x sub 1, which is -1. Notice I use parentheses whenever I substituted. Because you know how we had to substitute a -1 for x sub 1? Kids sometimes forget, oh, I'm already writing down a negative here, so I'll just write 2 minus 1, which is incorrect. So notice all I did was I kept the same structure, just change the letters into parentheses. And then you calculate, you go home and be happy. So that's what, -4 over 3. I can't simplify it. So there's my slope. Easy peasy, right? Just following the formula. But calculating slope, okay, great, we did it. But how does that help me? What is a slope of -4/3? Why do I care that the slope of this line is -4/3? Well, it turns out that lines are classified based upon what slope they have. So let's talk about the classification of lines. Because without graphing, if you know what the slope of a line is, you can visualize, you can already describe what that line is. So the idea is that the slope of a line indicates if I can spell, whether the line, and here are the following options. I really wish I could write italicized, but I can't, so I'll go ahead and highlight it. Rises left to right. That's one option. A line could falls from left to right. That's another option that line could be. A line could be perfectly is horizontal. That's one possibility. And using process of elimination, we know the other option has to be vertical. So those are the four classifications or four things a line could be. A line could rise from left to right. It could fall from left to right. It could be perfectly horizontal flat, or it could be perfectly vertical up and down. If you guys know, there's no shame in it. I have pre-calculus students who have to take a moment and go, okay, what is horizontal again? Let's just quickly draw these pictures out here. So I'm not going to draw a coordinate grid. I'm pretty sure you guys can imagine a coordinate grid. But something that looks like this would be considered rising. This is a rising line. Something that looks like this would be considered a falling line. This right here is horizontal. And this like here is vertical. But again, how does calculating slope help me determine what is which? If you have a rising line, those slopes are always positive. If you have a falling line, those slopes are always negative. If you have a horizontal, which, oh, that was ugly. Horizontal. If you have a horizontal line, those are always zero slopes. And if you have a vertical line, those slopes are undefined. If you don't know what an undefined slope is, that simply means your slope is some number divided by 0. Right? So that's how you get undefined slope, if you have some number divided by 0. So yeah, we could easily tell if a line is positive, negative, 0, horizontal by just graphing it. But you know what? That means you had to draw a coordinate plane. You could draw tick marks. That's a long time. By analyzing the slope, we can easily visualize what the line is doing by simply doing algebra. So for the previous example, this example here, we would classify this line as what? This line is doing what? It's falling, right? That's what I'll just say. So if the question says, classify the line that goes through -1, 3, and 2, -1, I would write, this line falls from left to right because the slope was negative. Easy peasy? Yeah. Any questions so far? Right. Analyzing slopes also allows you to classify two special types of lines. So in the world of algebra and geometry too, you talked about these two special types of lines. So special lines. When I think of special lines, I think of the following. I think of parallel lines. Geez, I need to learn how to spell. Parallel lines. And if you guys remember from geometry, definition of parallel lines, two lines that never touch. Two lines that never intersect, two lines that never touch. Right. If you really want to blow your minds, once you guys go to college and take like advanced geometry, you'll actually find that parallel lines do intersect eventually. Yeah, but for our purposes, for high school math, parallel lines never intersect. Yeah, they intersect at infinity, yeah. Which is a really trippy thought. Okay. So, quick example of two parallel lines. Lines, if they're special, can also be perpendicular. Now, perpendicular is probably the word you guys use in geometry. Once you get into like higher algebra, we have like a bajillion different names for perpendicular. So perpendicular is the normal, is the, pun if you guys know math. Perpendicular is the normal term, but you may also hear these terms here. AKA, and that's why I was laughing, normal. So normal lines means perpendicular, or orthogonal. Right. So you may hear those terms, they all mean the same thing. Perpendicular, normal, orthogonal, they all mean the same. Yes?
I was taught ortho means both. How come perpendicular ortho? Like, why is it
Ortho means what?
both?
Bone?
Bone or straight?
Oh.
Yeah.
Oh, that's a very good question. Can I this is a completely educated pulling out of thin air guess. You said ortho means bones or streets. Well, our streets are in a grid system, so they intersect perpendicularly. So maybe that's why they use it. That's a complete guess. I'm just making it up. Yeah. But the geometry definition: lines that form 90-degree angles at their intersection. Right. So that's the definition of perpendicular lines. They have to be a perfect T. It has to make perfect 90 degrees. If you're at 89 degrees, sorry, you're not perpendicular. So there's an example of two perpendicular lines. Again, yeah, we can totally tell if lines are parallel or perpendicular by drawing it out, but that requires you to have ruler straight edge, that requires you to have perfect tick marks. That is a pain in the butt to do, to draw, especially if you don't have grid paper. Fortunately, we have algebra to help us. So how can I know if lines are parallel or perpendicular if I just have their slopes? So the idea is this: two different lines. Hey guys, can we not talk? I mean, I personally don't care, but I'm pretty sure the people who are watching these videos don't care about your conversations. Two different lines. I made them public, by the way. I unlisted them. Two different lines are parallel if and only if, you guys remember that from yesterday, IFF means if and only if and only if they have the same slopes. Right. So the connection, the thing that you should be connecting in your brain is parallel connects with same slopes. The idea for perpendicular: two lines are perpendicular and I have a slight suspicion that mathematicians made the word normal to mean perpendicular because they get tired of writing the word perpendicular because it's a pain in the butt. Two lines are perpendicular if and only if they have opposite and reciprocal slopes. So the thing that you guys should glue or connect in your brain is, if you think of the word perpendicular, when it comes to slope, you should be thinking of opposite reciprocals. What are opposite reciprocals? For example, if I had a slope of 2, I guess you should do m's. M sub 1 equals 2, and m sub 2 equals negative 1/2. One's positive, one's negative, so they're opposites. One is a 2, and the other is a flip of the 2, 1/2. They're reciprocals. These guys are perpendicular.
Mr. What is MG?
What is what?
MG. I mean EG.
Oh, Egypt, for example. Yeah. It's a Latin phrase. I believe it is exempli gratis, but don't quote me. It stands for exempli gratis, which means like a free a free example. When I use EX, that's an example we're going to solve. When I use EG, that's just an example I'm putting there just to showcase something. Yeah. I know, it's weird. I'm weird. That's just what I do. Yeah. So you're okay with the relationship between the slopes and parallel perpendicular lines?
Yes.
All right. The last thing I want to do with you guys is vocabulary. If you hear the phrase average rate of change, it just means slope, right? You typically use the word average rate of change if you're doing a word problem, and I know you guys freak out, oh no, word problems, this is hard. But if they use average rate of change, it's just a slope problem. So let's do an example. And yes, I must warn you, it's going to be a word problem. So suppose in 1965, the diameter of a giant sequoia, it's a tree, was measured, the diameter of a giant car was measured to be 137 inches. That's a pretty big tree. Yeah. In 2005, the diameter of the same tree was measured to be 141 inches. Find the average rate of change. Now, I'm going to be lazy. I'm going to abbreviate average rate of change, AROC, AROC. Find the average rate of change in the diameter of the sequoia over time. And hence, predict its diameter in 2065. That looks intimidating. A big wall of text, lots of words. I know you guys don't like word problems, but once I hear the word average rate of change, I go, oh yeah, this is just a slope problem. We got this. This is easy. Now, the reason why I think average rate of change word problems are easy because they tell you the answer or they tell you what to do. Notice this phrase here. Find the average rate of change in the diameter over time. Slope is rise over run. They're telling you to find the average rate of change of diameter over time. So you know the slope formula, y2 minus y1, blah, blah, blah. Guess what type of information we're going to put on top if it says diameter over time? What goes on top? The diameter. What goes on the bottom? The time. Easy peasy. So all I have to do is find those two pieces of information. We're going to have to build relations. What we talked about yesterday. We're going to have to build relations. We're going to have to link up information in this particular problem. Do you guys agree we're talking about diameters and time? So let's link up diameter and time. So reading the question, they gave us 137 inches. That links up to what time? 1965. They gave us 2005. That's a time. That links up to what? 141 inches. So what we can do is convert these pieces of information into points. Now we have to be very, very careful here. Do you guys agree? Actually, I guess I'll just write this down in case you're looking at this video in the future. We agree in m equals y2 minus y1 over x2 minus x1, that we're going to put the diameter on top and the time on the bottom. That's what we just discussed, right? In math, the triangle symbol just means change. So this is change in diameter on top, change in time on the bottom. So question?
What you guys earlier, what is it like, why did they say delta?
Oh, that's just the name. That's how you pronounce the. If you study Greek, the Greek letter for delta looks like a triangle. Yeah.
He's running.
So, knowing that the diameter is the y and the time is the x, when I do these linkages here, I hope it's not a big stretch of the imagination that my first point is 1965, comma 137. Is everyone okay with why I did that? Because we said that the time was x, so I put it first, comma, the diameter was the y, which is the 197. So when I do my second linkage, what's my second linkage? 2005, comma, 141. Hey, we have 2 points. I'm asking you to find the average rate of change. Average rate of change is just slope. We have the slope formula. We're done, right? Just plug it in and be happy. So the only difference is instead of doing m equals, because it's not slope, it's average rate of change equals y sub 2 minus y sub 1 over x sub 2 minus x sub 1. And then all you have to do is, well, math. What's that? Is that going to be 5? No, 4. 4 inches over 40 years, which is 1 over 10. So it's 1/10 inch per year. That's the average rate of change. So that's the answer to the first part. So we're not done with the whole problem because they also ask us, predict the diameter in 2065. Well, you already know that on average the diameter changes 1/10 of an inch per year. So what was the very last year that they gave us? 2005. So we need to ask this question. How many years between 2005 and 2065? And the answer was 60 years. If you know it changes 1/10 of a year, or 1/10 of an inch per year, and we know we want to predict, yes?
If you put 2065,
Yeah, that's what the
they
question.
said 1965.
Oh, I'm sorry. If I said 19, I meant 20. 2065. Yep. So this is more of a common sense thing. We calculated that's changing 1/10 of an inch per year. We want to predict 60 years into the future. What do we do with those two pieces of information? You multiply them, right? Therefore, in 60 years, we predict the tree's diameter will change by 60 times 110, which is 6 inches, right? Now, when you use a slope, your answer that you get is not going to be the final answer. It only gives changes. So I want to make that clear. Slopes only give changes. So to answer the question, predict the diameter in 2065, the answer is not going to be 6 inches. That's not the diameter. It changed by 6 inches, right? So the diameter in 2005 was 141. We predict it's going to change by 6 inches. Therefore, the true answer, the diameter, is going to be 147. Therefore, the diameter is 141 plus 6 equals 147 inches. So those are the two answers to that question. Find the average rate of change and use it to predict the final diameter. By using the average rate of change, we only find the net change. So to get the actual answer, we have to add it on to the last diameter. Questions? So that's all slope does. Slope just calculates how much something changes with respect to another variable. I don't care if I tell you to find slope. I don't care if I tell you to find average rate of change. All it is the same slope formula. Right? If there's one formula you know, it's that guy. Alrighty, that is it. That is 2.2.